This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Good evening, everyone. Welcome to Science at the Theater, sponsored by the Friends of Berkeley Lab. My name is Jeff Miller. I'm head of public affairs at the lab, and I will be your host for tonight. Well, tonight is election night. You guys and those joining us on our live stream will be able to vote for 5 Berkeley Lab scientist candidates who will have 12 minutes and 12 minutes only to convince you that their technology has the greatest benefit to society. Okay? That's the criterion for tonight. There will be no party affiliation mentioned, so you can't use that to guide you. For purposes of tonight, let's say that they're all members of the Better World Party, which is not a bad idea. You have to assume that all the technology is scalable, ready for mass market, that has commercial potential, that it's very cool, and that it's in keeping with the mission of Berkeley Lab, which is to bring science solutions to the world. So, again, when you're voting, it's about social benefit, not commercial potential, not because that isn't important, but it's beyond the purview of this evening. I would like to tell you as well that our Eureka restaurant in Berkeley has offered prizes to tonight's winners. They are over on Center Street nearby, and I believe they're open till midnight, so if hunger strikes you when the meeting is over, when this event is over, please feel free to go there. And thanks to the folks at Eureka for donating the prizes tonight. Now, I would like to spend just a second to tell you about another thing we're doing tonight that's unusual, and that is that we have 3 judges to help us decide which is the best technology. Now, these judges are not Shark Tank kind of judges. These are picked for not their nastiness, but for their smarts. Their goal is to offer kind of a friendly reality check for the scientists. So you have their names on your program as you hand it out. I'm now going to bring them out, and please give them a warm welcome. Robin Johnston from Berkeley Lab, Braden Penhote from UC Berkeley, and Peter Fisk, CEO of Paxwater in Richmond. Braden's on your left, Peter's on your right. Now, the real fun tonight's going to come at the voting moment. So we're going to have the audience and those online vote first. And when that's locked down, we're not going to reveal it. We're going to then be talking to the judges about their choice. And they will reveal their choice. And we're going to see then if there's a difference between the judge's choice and the popular choice. And we may have 2 winners. I mean, everybody's a winner, really. But this could be our little point of artificial drama, if you like. And so we hope that you enjoy it and find it fun. There will be a question and answer period at the end. Microphones are here and upstairs. There probably is not going to be a huge amount of time for Q&A tonight. This is a very packed program, but we will do it, I promise. Lastly, after this event, Science at the Theater is going to go on the road. We haven't picked our venues yet, but if you look at the Friends of Berkeley Lab website, which is, if you go to lbl.gov, you will see the tab for Friends of Berkeley Lab. You can join Friends of Berkeley Lab, get our regular emails, and so you'll hear about where our venues are going to be. And it's a good idea to stay in touch with us in any case about all the wonderful science that's going on. I think that's it for now. Judges, are you ready? You ready? Are you getting excited?
Oh, yeah.
Okay, so let's start. Our first scientist of the evening, Sylvain Costas, who's going to talk about why hacking our DNA is maybe a good idea. Welcome, Sylvain.
Well, thank you for being here. I'm going to talk to you about DNA today. So the Berkeley Lab has great expertise in the field of radiation biology. It's the field of understanding how radiation impacts us, humans. Radiation is that thing that we can't smell it, we can't see it, we can't feel it, and still it's around us in this room right now. And there's a tremendous amount of fear around radiation. So the DOE and NASA have spent a lot of money trying to understand this effect, and we've been studying it for 30, 40 years. So Fukushima recently has brought radiation back on the stage, but you can see here that also the New York Times has played a tremendous role in creating this fear of radiation. This is the latest of the New York Times which basically is telling us that medical imaging gives us cancer. And this is the kind of things that we, as scientists, try to address in a rational way. So this is DNA. It's a double helix, and there's 2 strands. And what we look at the lab is what we call a DNA double strand breaks. Is when the 2 strands of your DNA gets broken, and your DNA then gets split into 2 pieces. When that happens, and this is an impact here of radiation hitting the helix, you have to repair it. And if you don't repair it correctly, you may get cancer through a mutation of very important genes. Now, this is an example here of a chromosome that gets 2 DNA double strand breaks. And if you don't repair them right, you may actually lose a whole chunk of chromosome. And if it's not vital, but important for the cells, you may have what we call an aberrant cell or a cancer cell. So this is the reason why radiation is such an important thing to look at and why DNA damage is at the heart of this cancer question. So I mentioned radiation, but it turns out that there's more than radiation that affects DNA damage. You have the environment, toxin. You also, what you eat, your nutrition. So if you take antioxidant, can affect your level of DNA damage. So as we're breathing in this room right now, we have a lot of what we call reactive oxygen species that are going to damage your DNA. That's why we take antioxidant to fight this effect. And so one thing that no one knows, but you get about 1 to 10 DNA breaks per cell every day for 24 hours. And we have about 70 trillion cells in our body. So every 24 hours, our body is fixing 700 trillion DNA damage. And it does it just fine. Except when it doesn't do it right, well, I mentioned cancer, but there's a lot of other diseases that has been linked to DNA damage, such as accelerated aging, neurological disorders, immunological disorders, and so on. We developed a kit at the Berkeley Lab that allows you to collect your blood at home. And basically, you can then put the blood into a tube and fix immediately when it comes out into what we call fixative that stop any biological processes. At that point, we have a snapshot of exactly how much DNA damage you have in your body. Then you send it back. We analyze it with state-of-the-art technology. And then we have software that automatically identifies the nuclei. And then if we look closer, we can see that, for instance, cell number 10 here, cell number 10 has no DNA damage, and this cell here has 1 DNA break. So that's the kind of technology we can do. We can do it very fast. We can look at hundreds of people a day. And what we've done is we tested this at a biohacker space. So it's a space where people test different ideas. And we had 67 volunteers who gave their blood. And this is what we saw. As you age, you have more DNA damage. Between the age of 20 to 70, you will double the amount of DNA damage. The other thing that's interesting here is that we have an example here of 2 persons that were extreme in the response. That was a 27-year-old male that had very low count. And in contrast, this lady had a lot of damage. OK, they place here on the graph. What's interesting, if you look at this graph carefully, what's curious is that within a given age group, you have a lot of variation. That's probably reflecting genetic diversity among us. Some of us repair better than others. But it's also reflecting the environment, what you do, what you eat. And so this is something you can take action on. If you zoom closer on this data, what's interesting is out of that cohort, there were 4 people who had cancer in their life at some point. They were still alive, obviously. And what you see here is that all those points are above the linear regression line, which means that they are above their age group. So it seems that it's also linking to cancer. So this is the schematic of the data. You have that linear increase with age. That's the number of DNA damage as a function of age. And this is the way you can use that. You get a CT scan, you're here, and you want to measure after you got your CT scan. If you didn't get a lot of damage, you can measure that, one application. Or you live in Fukushima, you want to see if you have a high dose. Option 2, you're pretty high, but you want to see if antioxidant can help you. So you can take antioxidant and see if you can go back to your baseline. Option 3, this is the holy grail for us, is the medical application. How many diseases will correlate to these measurements? It's an open question. So again, to summarize, we have an environmental surveillance system. So this is kind of like what we call tracking DNA damage. You also have a way to optimize your health with this device. So this is more the hacking part. By being able to track over time, you can take action and change it. And finally, I think on the long run, we're going to have a tool for disease prevention. So now, how do we do this? We created a startup that is actually trying to address this point. The kit is now available. And we have what we call a citizen science campaign. So what that is that we let the people go online, get the kit, and test it, and enter a lot of information about how they got the data. I mean, were they having antioxidant before they took the test? This kind of information. And when we did that at BioCurious, at the biohackerspace I mentioned earlier, there was a lot of enthusiasm because people were like, I want to see how I can hack into my DNA health, and I want to see how I can optimize myself. So action taken based on the measurements. And so this is the current campaign. We're actually online right now. I put the link, and the startup that we created is called Exogen. It's a very early stage startup. And I think we have a lot of dynamism. We have a great team, and the Berkeley Lab has been very good at pushing forward this kind of idea. So with this, I hope you can join us, and I'd be happy to answer any questions.
Great, thank you. I have a question before the judges. Does this mean that we should be eating blueberries before we have a CT scan as a protective device?
You are so smart.
Organic blueberries?
No, this is true. I didn't mention that, but there was an experiment done in Germany where they did exactly that. It was not blueberry. They didn't say what they gave them. It was something probably more potent. They call it the radioprotector. And they didn't do that on people who got exposed. They actually take their blood. They had two groups, one group that was having this radioprotectant and one group that did not have it. They took their blood out. They exposed the blood ex vivo in an X-ray machine. And then they used this assay to measure the amount of DNA damage. What was really remarkable was the people who were taking the antioxidant, the radioprotectant, I should call it. It took them about 1 hour to get the maximum benefit. And for 1 to 2 hours after the antioxidant, they had an amazing lower level of DNA damage from the radiation. So if there's one home message, is one.
Okay, so judges, I'll give you another minute. That was my question. So, please. Okay.
I have to say, blueberry futures have just spiked on the internet.
That's what I'm investing in.
Yes, I bought some earlier today.
What an exciting way to not just look at your genetic record of damage, but also to get a response and to be able to take action in your life that might actually be measurable to improve your life. Very exciting.
I have a question for Sylvain. Yeah, I love that aspect that Peter already brought out. But the assumption here is that knowledge alleviates fear, but knowledge also causes fear. So this is obviously a diagnostic, not a therapeutic. Can you use this technology to find things that we don't already know that we're supposed to do? We know we're supposed to have antioxidants. We know we're supposed to run. Some of us will do it and some of us won't, as we've seen from diabetes studies, et cetera. So can we use this to fine-tune, should we be eating avocados or blueberries, or should we be running or walking, et cetera? So I'm kind of interested in the next steps.
Totally. So it's a very good question. I think the big question is, and that unfortunately we're not investing enough money in this kind of research, is the long-term follow-up of people. So you take this biomarker, and the power of the biomarker that we have in place here is the long-term follow-up. So for instance, having too low level of antioxidant has been, if you take too many antioxidants, you have a low amount of DNA damage. There's been some recent study that seems to suggest that if you're too low, you end up having an issue also for your health. And the concept here is kind of like you need a bit of arm in your body, just enough to stimulate the response and have a natural antioxidant uptake in your body. Seems kind of counterintuitive. So basically this kind of assay, for instance, if you know where you are, it'd be interesting to see if the people who are in the norm are the healthiest or the most protected for long-term disease. But that can only happen if we track for a long period of time. Unfortunately, there is no fast bullet here. And that's why, the NIH, a lot of those institutes are not very fond of this kind of research, and that's the reason we took it to the public, because we felt the NIH and other institutes are going to have a very hard time launching such a long-term study. And I feel like if we educate the people about this kind of tool, they're not cheap, but if we do a lot, we can make it lower cost, and we can maybe start approaching this. But this is long-term investment, kind of like Google. When they started, they had very little data. They were not that powerful, but as they build up their database, you can see now how amazing they are, right?
Great. Okay, Braden, did you have a question?
Yeah, I have a question and kind of a follow-up marketing idea. The question is, you test the blood taken from the fingertip, and it's radiation-caused DNA deletions are site-specific. So I'm curious the relationship between what you find in a drop of blood from your finger and what may have happened to your brain in a CAT scan.
Oh, yeah. So there were some studies done on mice showing that if you look at these kind of markers, they took mice that had very different genetic backgrounds. Some were very sensitive to radiation, some were very resistant. And they were looking at the blood and at the brain. Actually, I don't know if they looked at the brain. They looked at other organs like the breast and the lungs. So they had like 5 or 6 organs. What was interesting is that no matter what organ they looked at, the animal ranked exactly the same way in every organ you looked at. The number changes because your blood has a lot of oxygen, so you may have more damage there. The breast is not very oxygenated, so you may have lower level. There's also cell type differences. Some cells have a different metabolism and show up more damage. But they still rank the same way independently what you look at. So blood is a great surrogate tissue that's easily accessible. Plus, it's really great because you can work on mice and on human and compare results.
Yeah. So I think it's not a specific deletion in a specific cell or organ that you're tracking. It's the aggregate damage from your exposures.
Absolutely. I'm sorry, I misunderstood your question. So that's
okay,
a very.
We're going to have to. Can we end it there? I'm sorry because
Yeah.
we have to keep. We have a lot of people.
Keep it moving.
So there are more questions.
Thank you. It's great.
We can ask at the close. Thank you all.
Thank you.
Okay, next up, making better batteries. Guoyin Chen. Please welcome her.
Thank you so much. It's such a pleasure to be here tonight to tell you about the technology we're developing at the lab, which is making batteries safer. So rechargeable batteries, they have come a long way. If it wasn't for today's lithium-ion batteries, your cell phone would probably still look like this. It's bulky, it's heavy, and certainly not very attractive. When it comes to packing energy in a given amount of space or weight, there is nothing really come close to lithium-ion, so that is really great. But unfortunately, this great technology also comes with some pretty serious safety problems. Now, battery-related fire and safety incidents have made headline news in recent years. Now, small batteries like those in your phones and laptops sometimes can catch fire. But the amount of energy in them are actually pretty small, so serious incidents are rare. And when they do happen, the battery industry is always very sensitive to it. In the past, major manufacturers have recalled millions and millions of batteries. Now that, of course, have huge financial consequences. In 2006, when Sony recalled 10 million batteries for laptops, that itself wipes out the company profit for that quarter. So there's a huge need for safety problems, and it actually gets worse. It gets worse when it comes to these massive batteries that are used on airplanes, like those on the 787 Dreamliners. That because you can't just jump out of or leaving a burning battery. Or electric vehicles, for example. Now, this GM Volt battery, it has 200 cells, weighs 400 pounds, and has an energy equivalent of about 60 dynamite sticks. Now, that only gives you 40 miles driving distance. If you happen to own one of those electric vehicles, then it has 4 times more energy. So you can see it's very large and very massive. Now, because of these high numbers of cells in these battery packs, the probability of something goes wrong is actually a lot higher than your small cell phone or laptop batteries. And also because the number of cells, the packs becomes really complex. And some of the safety measures that you imagine you can use for small batteries, they don't apply here. So what is really causing all these problems? Unfortunately, these safety problems are intrinsic to lithium-ion battery chemistry. Now, a typical battery will have a positive electrode and a negative electrode. Positive is usually some kind of metal oxide, whereas negative is made of carbon. These 2 electrodes acting as hosts for lithium ions to go back and a fourth, and that is what makes the battery rechargeable. When you charge the battery, what happens is that you're basically driving the lithium ions from the positive side into the negative. Now, there are many things could happen when your battery is fully charged. One of the scenario is that your negative electrodes simply run out of empty seats. No more place to put lithium ion. So that's when your battery is fully charged, and you should stop charging it. But in some rare incidences that you actually keep on charging it, what happens is that now you are into this stage what we call overcharging. Now that is extremely dangerous because your battery gets really hot really quickly. On top of that, these lithium ions that didn't find seats in the negative electrode now actually grow as highly reactive lithium metal inside the battery and form what we call dendrite. Now dendrites are very fluffy, so they can grow very fast, and sometimes they grow to the positive electrode. And when that happens, you have a short circuit, and that's inside your battery. And that is really bad because the short circuit will just release all the energy in the battery at once. And you can imagine that's a pretty violent event and involve fire and explosion and all that. The only thing that's standing in the way of this dendrite is a piece of plastic foam called a separator. Now, separators are very thin. So in the commercial batteries, they're about 20 microns thick. So think of your standard office printer paper, but 5 times thinner. And because they need to allow the lithium ions to go back and forth between these two electrodes, they have lots of holes. And in fact, about 50% of its volume is made out of holes. So separator is in no way to stop dendrite. So what can we do about it? The key to our solution is a type of plastics we call conducting polymer. Now, these are not your everyday plastics. You think of them as great insulators, like electrical tape, for example. Now, for these polymer, they actually have very unique properties. When you apply a high voltage to these conducting polymer, they can actually switch and turn into materials conducting electricity. I'm going to show you is a video clip actually capturing this transformation. Of course, you cannot really see the change in conductivity with your naked eye. It happens that these polymers have color change that associated us with these conductivity. So at the bottom here is basically a color index. Tells you how conducting the polymer is. Red being insulating, whereas blue is highly conducting, like a piece of metal. So, let's see. When we apply a high voltage to this piece of polymer foam, you can see initially it was red, so it was insulating. But it quickly switched to this blue color, and meaning it's really conducting now. And then it stays in this conductive state afterwards. So these are very unique properties. So the technology we develop in the lab allows us to put these conducting polymers into the battery separator. Now, because the polymer only becomes conducting at a high voltage, so you can expect that the battery is going to charge and discharge normal, but only when it is being overcharged, the voltage rises high, and this polymer becomes conducting and therefore start to carry the electricity and prevent overcharging. So does that work? Actually, it does. Here is a battery performance plot with the voltage and the capacity. I'm going to show you is what happens when you have a regular piece of separator. You're seeing the voltage slowly goes up, and that's during the charging period. But when it's overcharged, the voltage shoots up really quickly, and that's when your battery goes into a dangerous state, and it's very, very big safety problem. And the same so, but if we use our separator, what you see here is that it basically does the same thing during the normal charge, but when it's overcharged, the voltage actually stays constant. It never goes beyond the safety limit. So in that case, overcharge is prevented. So you see, it actually is a lot of work to make batteries boring. No sparks, no fireworks, definitely no explosions, and that is what excites us. Thank you very much.
Thank you for that great primer on batteries. So Braden, we'll start with you this time since I cut you off so rudely last time.
No, I mean, I think there ought to be a law that this should be required in all batteries. I'm excited. What's the fix right now? So when the Boeing Dreamliner batteries burned up, what did they do? What's in between bad and good?
I can't go into details too much about what they did because I think there's a lot of big engineering stuff going on, but the bulk of it is that they put a big container around it so that when the battery actually has fire and will go to overheat it, and somehow they're trying to contain it. So the problem's not solved, but it's...
that gives you a lot of comfort, right?
Okay, remember to look this way. Robin, do you have any questions?
So I understand that this, possibly is going to solve the safety issue with the separator, but is it also going to enable us to get to greater power or energy density because of these conductive polymers?
Yes, one of the aspects that I didn't mention is that these polymers actually can help the life of the battery, especially when you have a big stack and has many, many cells. You can imagine that not all the cells are going to be the same. Some of the cells are going to be weaker, which means that they're not going to have as many energy in it. Some are going to be stronger. And you string them together, make a big stack as a whole battery, and use them the same way. And these weaker cells are going to get used a lot more than the regular good cells. And so these weaker cells are continuously being abused. And so with these polymer in it, it helps them to balance the whole stack. In that case, that the weaker cells don't take the beat when things are running, and they just kind of let the polymer carry some of the load. So it helps to help the overall lifetime of the battery, and also, like you said, the power.
Peter, question?
Yeah, I just want to know, are you talking to battery manufacturers yet, and what are they telling you?
We're starting on that. This is a pretty early stage right now. This is mostly laboratory technology, and we're working on scaling up and working with partners to get to the point where it can be tested out in a much larger scale.
Okay. Okay, great. Gwen, thank you very much. So remember, everything is already scalable. So even though, okay. So next up is Alex Zettel, who's going to be talking about a very exciting new material. Alex?
So which one do I push? The advanced right here?
Yeah.
Great. Okay, good evening. I'd like to tell you about dress code for Martians. Actually, the reason I picked this title is this is a competition, and I figured I'd use a flashy title to get some votes. Okay, but I'm going to talk about materials. And materials are critical to civilization advancements. In fact, entire eras have been named after materials. The Stone Age, where people took stone tools, stones, and chiseled them into tools. And then one has sort of structures like aqueducts made by the Romans that used stones, very important engineering constructs. Bronze Age, that was much more complicated than just picking up rocks. You had to take ore, refine it, alloy it. You took copper and tin and alloyed it together. And even today, there's a picture of a modern ship propeller made out of bronze. So these technologies persist into modern times. And the Iron Age, this is a Damascus steel sword using iron that's been carbonized and properly tempered. Here's the Golden Gate Bridge, again using steel. So we see that increasing utility goes here, but that follows with increasing difficulty of synthesis. And the question is, what's next? What's the next age beyond the Iron Age? And if you're in information technology, you might say, well, silicon is it. Silicon runs our computers, so we're in the silicon age. If you're a biologist, you say, no, DNA is the most important thing. We're in the age of DNA. So to have a glimpse of what's next, what's around the corner, we look at Martians, okay? And in case you missed it, the Martians actually came to Earth in 1996. This was memorialized by a forgettable Hollywood movie. And here's a picture of the Martian. It's a little hard to see, but they look a little bit like my grad students. They have huge brains. They're incredibly smart, and they're wearing this bizarre clothing. It's sort of luminescent and so on. Here's their spacecraft. It's got some girders in here. And what allowed them to come to the Earth, and then they had a big fight with us, but we got them to leave. And they went back to Mars safely. What allowed them to travel? What are the materials that are constituting this clothing, the spacecraft, and so on? So we're going to see what's around the corner. What did the Martians use? Here's a picture of the periodic table of the elements. And in fact, on Mars and everywhere else in the universe, we have the same elements. We name them differently, perhaps, but this table is universal. And we have a whole list of elements. You could make an infinite number of compounds with this, so it's kind of complicated to figure out what are the best materials for the sort of next generation applications. We've got some exciting stuff down here like berkelium, californium. So those are exciting elements, but they're unstable. That stuff is way too far down, way too heavy. So the action is way up here at the top. These are where the elements are very light. And we want lightweight things if we're going to do space travel or have other similar applications. In fact, this first row is critical. And here's carbon. Carbon, the element of life, and many polymers and so on are made out of carbon. So that's where it's at right now. But what is the next thing? What are the elements that are really going to make the new materials? And I've circled two. And you just have to remember these two things, B and N, BN. Boron, nitride. Boron and nitrogen in a 1-to-1 ratio form a new compound, and that compound has spectacular properties. So here we look at where we've been in the past with carbon. Carbon forms the basis of our natural fibers, cotton, wool, silk, hemp, even synthetics, things like nylon, polyethylene, all these nice fibers that are made by our chemical industries, they're carbon-based, carbon chains. Even graphite fibers, sort of the most modern materials, the strongest materials that are currently being used for spacecraft and in automobiles, sports equipment, and so on, that's all just pure carbon. So here, this boron nitride, all these different incarnations of it, that's where it's at. That's what I want to tell you about. This boron nitride, this nanostructured boron nitride, is the strongest, lightest, most thermally conducting, most chemically resistant fiber that's known. Okay, it's a synthetic material. Nature has never figured out how to make this stuff. It's too hard. It's made in the laboratory. It was first predicted by Marvin Cohen at Berkeley, first synthesized in my laboratory at Berkeley. Here are the boron and nitrogen atoms forming this, and boron is blue, nitrogen is gold. There's a reason for those colors, blue and gold, right? Okay. This is what the stuff looks like. It looks kind of like cotton. Don't confuse it with cotton, though. It's a very different fiber. It has these interesting properties. Actually, this Mars mission, or traveling to and from Mars, is not just a joke. NASA takes this very seriously. And NASA put a lot of effort into the original Apollo space program to get to the moon, then the space shuttle program, and then the space station program. And they've gotten a lot of pressure to look seriously into sending a person to Mars and bringing that person safely back. It's a formidable problem, a very strong, tricky technical problem. And they looked at materials that might be used to send a person to Mars. So this is a serious study, and what we have here is sort of engineering terms. This is how stiff something is and how strong it is, and the bottom line is this is a good quadrant. Materials up here are really good. Materials down here are inferior. They're not good. And there are lots of different materials here, and there are ones that are being used already. They're flying. Other materials that are sort of around the corner, and then these ones in red are kind of the exotic materials that are being explored but are not in common use yet. So this is at room temperature. But for this space travel, you actually have to go to high temperatures, and rockets, engines go at high temperatures, and other components get heated up. So what happens at high temperatures, and what happens is almost all the materials that NASA knows about, is even contemplating, fall off the chart, except in the good quadrant, there's that one material, this boron nitride nanotube. NASA knows about this material. They say that's the only material that will get someone to Mars and back, okay? No other material can do it. No other material, no other exotic alloy that you know about will do it. So here's sort of an engineering comparison that looks at these different properties. Has to be lightweight, energy absorbing, high temperature resistance, strong, even neutron absorbing. There's a lot of radiation in outer space, and in fact, radiation, if you're flying an airplane right now, pilots flying polar routes aren't allowed to fly as often as pilots flying equatorial routes. They don't tell passengers about that. So you'd like to have materials that constitute spacecraft or airliners that absorb this kind of radiation. All these interesting materials have various properties and are good for some things, but boron nitride, this black means good, all the way across the board just beats all the competition. So, okay, this might be good for aerospace, but what about general impact to society? Lots of different fields. Could this be useful? And here's a partial list of why this might be useful and be broad-based. I've already talked a little bit about radiation shielding. It turns out boron nitride, this material, is very compatible with cell growth. You can regenerate nerves by growing them on a boron nitride scaffold. It doesn't happen with carbon scaffolds. In fact, cells love this stuff, and it's been used in radiation treatment. The cancer cells gobble this stuff up, and you hit it with a laser, it heats it up, and it destroys the cells specifically. Boron nitride stores hydrogen better than any other material. If you're going to a hydrogen economy, trying to lower your footprint, carbon footprint, boron nitride is the stuff you'd want to put in the tank. It works for water purification. Take salt water or dirty water, contaminated water, push it through these boron nitride nanofilters, and it comes out clean. Lightweight, I've talked about. Actually, the next generation airliner, they're talking about having the entire roof of the airplane be clear so you can see out at night, don't get bored. You don't want the radiation to come in. That would be a boron nitride sheet, which is transparent. It's the only material that can withstand that kind of differential pressure. High temperature resistance for jet engines. Electron field emission. You go to Costco now, they've got this power-hungry stuff on the flat panel displays. Boron nitride field emitters can go with 1/10 the power for large flat panel displays. High strength, let me just finish up with this thermally conducting. It's highly thermally conducting. That's the way to get the heat out of integrated circuits. People have talked about using diamonds and so on to get the heat out. This material gets the heat out very efficiently. And it has a tunable band gap. That's something where you can turn a knob and change the electrical properties of the material for solar cells. So this is just a smattering, and BN is at the center of all this. It's really an amazing material that has yet to be fully exploited. So let me finish up with this picture. It looks kind of like cotton. That's what the production looks like on Mars, I imagine. And right now, on Earth, our production is limited. It's easily scalable. That's where we should be going. Thank you.
Thank you, Alex. All right, so judges. Robin, question for Mr. Zettel.
Yeah, that's a great technology. That's so cool. So from what I remember, boron is a rare element. Is that true, and will that impact the societal impact of this technology?
No, it's not. Boron is not that rare. It is rare in certain parts of the world, but actually there's a lot of boron in California, in the Mojave Desert. And there's a lot of boron in other countries as well that we should get friendly with in a hurry. Okay. So
are they friendly countries?
They are friendly to us right now, yes. And nitrogen is just in the air. So these are both non-toxic, cheap, and not that rare. They're plentiful materials, plentiful elements.
Peter?
Yeah, so diamond's also a wonderful material, and we can make diamond, but it's very expensive. It requires a lot of energy. So it would be great if you could make boron nitride cotton balls and grow them in the fields. How do you grow your boron nitride?
If we don't grow it out in the field, nature isn't so friendly to making that because it requires very high temperatures. But in fact, it's pretty easy to do. You have a non-equilibrium plasma. You can basically send some gases in, and boron nitrides come spewing out. So it's a synthetic process. It does take some effort. And for example, Kevlar, which was discovered by DuPont, was found in a laboratory, and they said, this is really hard stuff to make. What do? Do we just drop it, or do we have a scalable process? And they put a fair amount of effort in to figure out how to scale Kevlar up, which was different from the original synthesis process, and then it became very popular. That's where we were with boron nitride. We figured out a difficult way to make it first. Now we have ways so the stuff just comes pouring out.
So how much have you made so far?
It's of the order of kilograms, which is large when you're talking about nanoscale materials, but what you want is metric tons, and that requires large factories, not a small laboratory.
Braden. Oh, wait, could you please? Braden.
So, amount of gray hair in the audience, I'm guessing most of you remember the Star Trek episode with the Horta. Remember, it was the creature on that planet that was silicon-based, not carbon-based, and only Dr. McCoy could fix it with, like, concrete or something.
Yes.
The question is, because silicon was just below carbon on the periodic table. What, in your view, is more feasible, a boron nitride life form or a silicon?
Well, I saw that Star Trek episode, and that was just total nonsense. There are no such things as rock monsters or silicon-based stuff, but boron nitride is a completely different story. Actually, boron nitride chemistry is not that well understood yet. There are entire books on organic chemistry in the library, all about carbon chemistry. And there are no books on boron nitride chemistry because the chemists haven't really thought about this yet. And I talked to an eminent organic chemist. I said, what do you think about boron nitride chemistry? He said, let me think about it a little bit. He came back a day later and said, I think it's richer than carbon chemistry. So I wouldn't be surprised if you could have some sort of interesting chemistry that emulates carbon chemistry, if you want to call it life, whatever, but the opportunity is there. We're just at the beginning of it.
Okay, Alex, thank you very much.
Okay, thank you.
So our next presenter, scientist number 4, if you're keeping track, Stephen Lanzazero, who's going to talk to us about a new stick-on electricity meter. Stephen.
Hi, well, thanks for all being here. So tonight I'm going to talk about how we can apply technology to help address some of the challenges we're facing looking forward. So a lot of human activity has had impacts on the world, and the kind of things that we've had and the advances in our life have pumped sort of a lot of pollution into our society. And what this chart shows on the left-hand side there is carbon emissions, annual carbon emissions, and on the bottom here is years, and what you can see is that carbon emissions, for example, have gone up dramatically over time. And this is just one type of impact associated with human activity on Earth. And the human activity has a measurable impact. One such measurable impact would be looking at global average temperature. But there are many other ones, looking at mercury levels in water and other kinds of things like that. And so what we face is a world in which we know we're having a lasting impact that will last for generations. And we need to figure out how we can try and mitigate our impact so that we can have a brighter future. So why does energy use increase? Energy use changes because we have improving quality of life across the world, including in the United States, but also elsewhere, in Asia and in other places in Africa. And in step with that, we have increasing industrialization and increased economic output. Okay? And these are really good things, right? People are living better lives, and that's something that we should all value and that we should be supportive of. To minimize the adverse impacts, however, of this increasing energy use, we really need to make some changes to the way that we operate our society. And the first thing that we can do is move away from fossil-based energy generation and move towards renewable energy like solar or wind or tidal energy or things like that. The second thing that we can do is we can convert from a place where we're burning fossil fuels, say, to heat your home, you're burning natural gas, to a place where you're using electricity to heat your home using an advanced heat pump, a very efficient way to generate heat. And that's called electrification. A similar one would be replacing your gasoline automobile with an electric car. And then the key part that comes after that is making sure that you operate your society as efficiently as possible and that that energy efficiency is persistent, that year upon year upon year, things are running as efficiently as possible. You're using as little energy to get the services that you need. So let's take a look at that problem a little bit. And what we've learned is that you cannot manage effectively what you don't measure. And so this chart shows, over on the left, annual energy use for a building in megawatt hours. So that's 1,000 times a kilowatt hour, and you pay for kilowatt hours in your house. And on the bottom here is years. So over the course of 12 years, this is the energy use of a building, annual energy use. And what you see is that over time, the energy use of this building increases, and it increases a lot. If you had just whole building data, if you just have whole building data, it's very hard to tell why that energy use is increasing. If you have a little bit more information about how much of that goes into lighting versus how much of that goes into plug loads like computers versus how much goes into heating and cooling, you can start to say, oh, well, look, it's the heating and cooling energy use that's increasing. And further, if you have even more information, so you have more measurement of what's going on in the building, and say there are 3 air conditioners in that building, and you look at the air conditioning energy use for the first unit, the second unit, and the third unit, you say, look, that unit 3 is consuming a lot more energy than it used to. Maybe we should look into what's going on in unit 3 and figure out how to make it more efficient again and save all of that energy. And this is really what persistent energy efficiency is about preventing what's happening in unit 3. And so we know that this is what's needed for a low energy future. So the energy savings potential here is by combining electricity metering, this measurement that I'm talking about, with software that automatically detects these faults in these buildings, and then the maintenance that drives the energy efficiency. But so how much energy savings are we talking about? Well, widespread deployment of this technology would save 15% of the US energy use if you just deployed it inside the US. That comes out to about $60 billion a year in savings and 50 million tons of carbon dioxide in savings. So let's just take a look at that just a little bit more. Over the next decade or so, if we don't do anything like this, if we don't apply this kind of technology, our electricity use will increase 10%. If we apply it widely so that our infrastructure uses this technology, we'll save 10%. And so there's a 20% difference between where we might end up and where we could end up. To just make that a little bit more concrete, if you take the total electricity use of the United States, and then you subtract the electricity use of these states, that's how much electricity we would save. So it's a really substantial energy savings opportunity. So how do we get these sort of what we call granular or very specific energy data? And the way that we do it is we install these kinds of boxes, and then there's all this complicated wiring around these circuit breakers, and we go in there and we install all these sensors in there. And it's kind of a little bit dangerous, and it's a little bit hard to see on the color reproduction here, but you wear a lot of safety equipment and you hire an electrician to do this work. And it just comes out that it's very expensive. It's very messy over here, as you can see. That means that you make a lot of mistakes. And as a result, it's just rarely done. So we don't collect this information, and as a result, these savings just don't happen. So how could we apply some science to the problem? Well, so this is what a circuit breaker looks on the inside. And sort of here, the current comes in here, and it travels up this piece of metal over here, and travels up here, and then back out. And so there's a changing current and a changing voltage due to the fact that we use AC power, so alternating current power here in the US. And so what my colleagues and I noted was that, well, maybe up here where the voltage and current is very close by, we could actually just measure some properties about changing electric and current and voltage at that point. And so it turns out that those changes result in changing magnetic and electric fields, which are measurable. And so we built a little model of the breaker here. This is the current path here in yellow, and then those blue lines represent the outside of the breaker. And we can run some simulations, then this shows what the magnetic field lines look like over that changing current in that breaker. And if we were to put a sensor in this little region where the red lines are, that would be right above where the current is, and we could use those magnetic field lines to estimate what the current is in the breaker. So maybe there's a better way. And this is a picture of an example of what we call a stick-on electricity meter that just sticks onto the surface of the breaker. And you could have that wirelessly communicate back with some sort of processing unit located right next to the panel. And this results in this very low-cost, easy, and safe installation of this technology, which could result in substantial energy savings. We've taken this and plugged it in a building. And what we have is this blue line is whole building electricity use. So it's a meter. It's actually the utility meter from PG&E. And we get high-resolution data out of that through a little agreement with PG&E we have. And then this green line represents the data that comes out of our stick-on electricity meter. And what you can see is a really nice shape relationship between our stick-on electricity meter, which is measuring just one circuit in this house, and the shape of the whole building power. The difference between these two is, of course, that the television's on in some other room or something like that. It's the electricity use being used elsewhere. But what we see is that we can very, very accurately measure the electricity use of any individual circuit very, very reliably, using this very simple technology that plugs onto the surface of the breaker. So to wrap this up, what we're looking at is that we really want to mitigate the human environmental impacts, and that's a serious challenge. In order to do that, we have to manage our electricity use very carefully, because we're going to be using pretty much all electricity looking forward. We're not going to be burning any fossil fuels, so we have to measure that in order to do a good job. And here at Berkeley Lab, we're developing technology that eases the installation and application of all of these great things that are happening, and that's going to make a big impact. So thank you.
Thank you, Stephen. Are these expensive to produce?
No, actually, they're much cheaper than the technology we use today.
OK. Peter, I think you need to start this.
So I think I have the name for your first product. So this is a circuit breaker, and it has a sensor in it. So it's the guilt trip. But I love the idea of every circuit breaker in your house talking to you and telling you what it's doing. And I imagine that when fully integrated into these breakers, it might actually be a standard that might be adopted. So hats off to you.
Robin?
I'm always the downer. What's up with this? I'm always asking the hard questions. So my question is, it's very, I'm not quite sure I understand who's going to take the action based on this. Is the individual homeowner, or is this mostly geared for commercial buildings? Because it's very hard to motivate consumers to chase pennies. I mean, if you throw pennies up in the air, nobody comes running, right? I mean, you have to throw $100 bills or $1,000 bills in Wall Street to get anybody to even flinch. So how are you going to motivate consumers to save pennies by turning their refrigerator down just a little bit? So what's the motive behind this to impact society, and how are you going to, cumulatively, obviously, this is going to could have a huge impact, as you showed, but individually, how do you motivate people?
Right. It's an excellent question. In commercial buildings, it's a little easier because the energy bills are a lot bigger, and so when you're saving potentially thousands of dollars a month, maybe that matters to you. But the bottom line is that this is a major challenge for the energy-efficient economy in general. And we've been trying to address it in a number of ways. One of the great ways that it's been addressed is through companies like what Solar City has done with solar, where they are essentially, you don't buy your solar panels. They buy them for you, and then they sort of pay you, essentially, to have them there. And so these kinds of market structures where a company would come in and apply a technology and actually run that, what's called fault detection and diagnosis, where they detect what the faults are. And then they actually earn revenue associated with detecting and correcting faults in buildings. And they collect part of the savings that the building owners have. This model is probably the most effective in at least the medium term for capitalizing on the potential economic value of these savings.
Can I have just one follow-up, really?
Yeah, go ahead. Go ahead.
Okay. So can you somehow integrate this with, I think people will make a decision once a year that I want to automate certain gadgets and things. is there a way for them to integrate some kind of decision-making into this system? I mean, once a year, so they say, look, if my refrigerator is using more than X, I want it to cut down, you know, at peak hours or something like that. I mean, because that seems like that would be viable.
Right, so the automatic aspect of it.
Yeah, some kind of automatic efficiency decision.
Right, that's absolutely part of it is, well, yeah, automatic detection of the faults is a critical part. And sure, you know, you don't want to be going and fixing these things every day. You know, it's something that part of a cycle would be done. And that's why having a third-party company do it is actually valuable, because they're going to be motivated to come out and fix the big faults first and only come and visit individual buildings once in a while. This isn't something that we're expecting that you're going to take care of in your home. It's something that needs to be taken care of on a more of a large scale.
Thank you.
Great. Braden?
Do you imagine that it would be optimum to integrate your invention in the manufacture of the breakers themselves, or is there some utility to being able to swap out, upgrade?
Well, so there are two ways to look at it. So for new buildings, sure, integrate this into breakers. Looking forward in the United States, the vast majority of our buildings are here. And so integrating them into the breakers, when I say they're here, I mean they're already built, right? These buildings are built right now, and they already have their breakers in them. And so going and replacing those breakers ends up having sort of many of the same complications associated with installing traditional meter technology. So there's really two paths here, right? There's new construction, in which case, sure, something integrated into the breaker is absolutely the right way to go. For the 95% of buildings that will be here in 20 years, they're already built today. So we have to address those buildings, and this technology is very effective for addressing that problem.
Great. Thank you, Stephen. Scientist number 4. Okay, next up is Gloria Oliver, and please give her an extra round of applause. Since she's last, that's always hard. She's going to talk about portable reusable sensors. Gloria.
Thank you for the warm introduction, and thank all of you for being here tonight. I'm a postdoc at Berkeley Lab, and I'm so excited to have this opportunity to share with all of you a really big idea we're developing in Dr. Ron Zuckerman's team. But first, let's talk about our daily life. We live in the digital age. Many of us have a smartphone in the palm of our hand right now. Every hour of every day, we're bombarded by email, tweets, text messages, Facebook status updates. It's like we're walking around in this cloud of digital information. But every second of every day, we're also immersed in a sea of molecules. Molecules like glucose, potassium, vitamin C are coursing through our bloodstream. We might even be exposed to unexpected molecules, such as contaminants in our drinking water, pollution, pesticides. And we can even imagine a scenario in which we might be exposed to harmful agents like anthrax or explosives. Fortunately, portable electronic devices have gotten thinner, smarter, and cheaper. But we need better devices. Devices that can detect molecules within us and around us in real time. Real-time detection of molecules will enable each and every one of us to make smarter, quicker decisions about our health, fitness, and safety. To enable this kind of technology, we need to bring detection out of the laboratory and into the real world, into the palm of your hand. But a lot of current sensing technology relies on biomolecules called proteins. Nature has evolved proteins to be very good at real-time detection. Take, for example, your nose. Our noses contain proteins capable of detecting a wide assortment of different odor molecules. These proteins let us know in real time if we're being exposed to a potential danger, like smoke coming from a fire. Antibodies, like the one shown here, are another class of protein that nature has created to quickly detect and eradicate foreign invader particles, like the flu virus or bacteria in the body. Since nature has already evolved proteins to be so good at molecular detection, why not just take some of these proteins, these antibodies, and try to integrate them into our portable device? Turns out it's not that simple. Proteins are extremely fragile, and they perform poorly when we take them out of their natural environment and try to insert them into a device. Proteins are also expensive to manufacture, so if we want to create this portable, cheap, reusable device that everyone can use or wear on their wrist, proteins are not a viable option from a manufacturing point of view. But what if we could create an artificial protein using more rugged building materials? To get at this question, we need to take a look at how nature builds proteins. Pieces of DNA, called genes or the genetic code, contain the instructions that nature uses to build proteins. This genetic code gets converted into a sequence of amino acids, which we can think of as just a linear strand of different colored beads, where each color represents one of 20 amino acids. The order in which these beads are strung together is important for biology, because when this strand gets put into water, it spontaneously folds into this precisely defined three-dimensional shape, which we call a protein. Proteins come in many different shapes and sizes, one of which is the Y-shaped antibody that you see here. And at the tip of the two arms branching out from the Y is where the action takes place. This is where the antibody detects and binds tightly to its target molecule. And if we zoom in a little closer on that binding site, we see that it contains a cluster of loops, which is a lot like what we would see if we were to zoom in on a tiny piece of Velcro. Nature has evolved loops to grab onto the target in the same way that we use the fingers of our hands to grab onto an object. We have been inspired by the way nature builds proteins and antibodies, and are working to transfer this method over to a synthetic system. Instead of using DNA, we're using robots and computers to design and synthesize protein-like materials. Instead of amino acids, we use much more rugged ingredients to synthesize an exact sequence of different colored beads. And we call this bio-inspired, more rugged sequence a peptoid. We have designed peptoid sequences that, when put into water, spontaneously assemble into these very thin, large surface area sheets that have tons of loops sticking out all over the surface. We call these sheets molecular Velcro. Molecular Velcro is a rugged, antibody-inspired material that you can roll out or print onto the surface of any portable electronic device. This is a photo of actual pieces of molecular Velcro floating in water after they've been stained with red dye to help us see them under the microscope. Compared to the size of an antibody, these sheets are gigantic, but they're way, way smaller than anything we could ever pick up with our hands. The section that I've outlined in blue here measures 50 by 100 micrometers in size. This is about the same size as the width of a human hair. Within this tiny section, there's 1 billion loops spread out all over the surface of the Velcro. So the loops are much smaller than anything we could see in this image with our eyes. But we know that the loops are there, because when we mix pieces of molecular Velcro with their intended target molecule that we've stained with a green dye, we see that the sheets quickly turn green, indicating that they're becoming coated in this green-stained target molecule. In these experiments, the target that we set out to detect was a protein called kinase, which is important for early detection of cancer. In closing, I want to emphasize that molecular Velcro is a rugged, antibody-inspired material that can be rapidly manufactured and chemically tailored towards virtually any target molecule. Our vision is to print pieces of molecular Velcro onto a tiny chip that can be loaded and stored inside of your portable electronic device, kind of like an app on your smartphone. By voting for molecular Velcro tonight, you're saying that you believe you believe in the power of this technology to transform public health. Because at the end of the day, everybody deserves the right to know what's going on in their bloodstream, and everybody deserves the right to drink safe water and breathe clean air. Thank you very much.
Thank you, Gloria. All right, Braden, let's start with you.
So what makes these more rugged than peptide-based proteins?
That's a great question. So it comes down to the actual chemical structure of these sequences of beads. There's a slight chemical modification in our bead strand that makes them a lot more stable and resistant to degradation.
Robin?
My colleagues are reminding me that this is not Shark Tank, it's Guppy Tank, so I'm going to back off. Actually, this is really neat.
I don't think you've been hostile at all.
This is really neat, and what I love about this is it's a platform technology, and also it's the nanoscale and the bioscale are now coming together in science. It's from 1 to 100 nanometers, and so DNA and proteins are about the same size as nanotubes. And so now we're going to see this integration of nano and bio that's pretty much the most exciting thing happening on the frontiers at Berkeley Lab these days and other institutions. So I think this is fabulous. I think it's platform. And I don't, you know, I maybe will ask you later about some more specific applications, but thanks a lot. I have no criticism at this point.
Peter.
So I'm in the water business, and when you said pure and clean water, that's very important to me. So tell me how you would apply this specifically to purify the water. One thing is detecting that the water is unsafe to drink, but do you have a vision for actually using this to purify water?
Yeah, so you're exactly right. One application would be to deploy these chips that have been coated with molecular Velcro into like a river or a stream so that we can continuously monitor whether the drinking supply is being contaminated. But another possibility would be to think of these sheets as like sponges, molecular sponges, and you could envision kind of releasing these out into a contaminated area and having the sheets act like a sponge that just soaks up all of the dangerous agents. So yes, we are thinking about those two different directions to take this. So it's exciting to see what's going to happen next.
Would that include oil in an oil spill? Sponges?
Perhaps, okay. Yeah. So one thing I didn't mention is that the interior of these sheets is very, very oily. So when you stick these in water, they become a magnet for oils. So you could use these as a remediation agent for an oil spill.
Okay, great. Gloria, thank you very much. Scientist number 5. Okay, so let's review. Okay, scientist number 1, Sylvain Costas, talking about hacking DNA, blueberries. Guoying Chen, scientist number 2, better batteries, safety, we don't want things exploding. Alex Zettel, scientist number 3, talking about this exciting new material that could enable space exploration and who knows what else. Scientist number 5, Stephen Lanzazera, talking about an important energy measurement device. And lastly, Gloria Oliver, scientist number 5, her molecular Velcro approach, which you just heard about. Okay, we're going to talk to the judges now and see what they think, and they're going to pick their winner of the evening. So judges.
Oh.
Judges. You guys ready?
Les juges.
Yes. So tell me, I'm just going to throw these questions out, and you guys can talk in general, no particular order. But so was there anything in particular that impressed you about the overall quality and the fact that these were all scientists from the same institution doing such radically different things?
Yeah, I think I'll start. The judges up here, you know, we noticed that 3 of these technologies are directly detectors, and knowledge is power. And so we were very impressed with how they also relate to one another. Sylvain's wonderful detector, if I am flying to Mars wearing my boron nitride underwear to protect my cells, I'll be able to know that my cells are safe because of Sylvain's cancer detector. And probably my spaceship will be made out of boron nitride too, with batteries, safer because of Goying's membranes. Meanwhile, my spaceship will be, I'll be checking my air conditioner on my spaceship and knowing that it is energy efficient, because in space that matters a lot. And then finally, I'll be able to just be able to basically pluck out of my environment any substance I want with my molecular Velcro. So I am ready for the next century.
And you won't catch on fire because your battery separators will be...
That's right.
All right.
So thank you, Lawrence Berkeley.
Lab. So what impressed you the most, Robin?
Oh, gee,
I mean, you don't have to. We're going to ask you your pick, but I'm just speaking in general right now.
Well, I mean, I agree with Peter. I left my mic on, but detection is power, but it's also not necessarily a solution. So sometimes it just generates fear and anxiety, et cetera. So I'm really interested in the next 5 years what some of these technologies, how they're going to actually bring solutions to some of the problems they've identified. And that's what happens at Berkeley Lab. Things that we detected 5 years ago now are the things that we've actually been able to solve for, because you can't detect, as Peter said, if you don't know it, you can't solve it. But anyway, but loved the venue and loved all the technologies, really. Yeah, there's something happened here. I won't repeat that.
Okay, Braden.
I just want to tell a quick story. Nook Barker was a professor of biochemistry. Barker Hall is named after him. It's on the corner of Oxford and Hurst, if you've ever seen that gray building. Nook Barker won the Presidential Science Medal for discovering how vitamin B works in your body. And the way he discovered it was he liked to hike, and he would hike up to LBL, and he'd get the radioisotopes that E.O. Lawrence and all those guys were manufacturing up there, and he'd take it back down to his lab, and he used it to track the molecules through the metabolic pathways. And so this story that came out really in the DNA and in the molecular Velcro, this synthesis that Robin talked about between physical science and biological science, is an important Berkeley story. So I'm like quite moved by that. And Nook was a wonderful guy. If any of you ever want to look up his bio, you might be touched.
Did he get cancer?
No, he didn't. That's a good question.
We'll hold those questions for the Q&A. So, Robin, you work actually at Berkeley Lab. So, do you find this kind of inspiring technology all over the place?
Well, so I don't know. Is this on again?
Why don't you borrow one of the others?
Let me just steal this. I work in the technology transfer office at Berkeley Lab, and we get about 180 inventions every year, and so many of them are just groundbreaking, and it's just thrilling to see it. I think when I started 10 years ago, we received 80 invention disclosures a year, so you can see that the appetite for actually producing inventions that have real impact on people and societal impact is really the emphasis, has increased dramatically since I've been there, and it's wonderful to see inventors actually wanting to engage a lot more with companies to make sure that not only are they making the fundamental science breakthroughs, but they take that feedback from companies about what the barriers are to commercialization for various things like the batteries, et cetera, and they make changes to their research sometimes based on that feedback. Even though we want to have breakthrough fundamental research, it's great to also stay in touch with the commercial sector and make stuff that's real. And I know, for example, Alex Zettel has met with dozens of companies over the years on his nanotube technologies. He's had nanotube radios, et cetera. By the way, he won the Feynman Award this year, so we can congratulate him for that as well.
Congratulations.
You know, it's just one example of these professors that, and researchers that come up with dozens. They have a portfolio of dozens of technologies, and it's a thrilling thing. And I encourage you all to keep track of what's going on at Berkeley Lab. It really is the future.
Robin, I think you should maybe claim credit. I think you said that from the moment you arrived here to now, the disclosures have more than doubled. That's right.
Okay, so now we're going to put you on the spot. So have you guys marked your boards? Have you picked your winner? Please do so, and then we're going to go through one at a time. Okay. So we write. Okay. 1, Sylvan, Guoying 2, Alex 3, Stephen 4, and Gloria 5. Okay, so I'm going to ask you to reveal, and then I'm going to have to ask you a quick explanation for why you chose that over some of the others. And we're assuming everybody's a winner. They were all great. Okay, and this is just for fun. Okay. All right, now. All right, ladies first. Ladies first. Robin, your choice is? No, not you yet. Robin.
Is your name Robin?
No.
Number 5, which was Stephen Lancesera?
Molecular
Gloria.
Velcro.
This is
Gloria.
supposed to be molecular Velcro.
Molecular Velcro. Sorry, my fault. Gloria? Gloria Oliver, number 5. So why? Why that over the others?
Platform technology, lots of applications, and I think we haven't seen the end of it or even heard a fraction of what that's going to accomplish yet.
Okay, great. All right, so 1 vote for Gloria. Since Braden showed his already. Braden, go ahead, show yours now.
No.
And I'll get it correct. Another vote for Gloria, number 5, molecular Velcro. And your reason, sir?
Yeah, I just think, we're exposed to so much stuff that we don't know, and we're manipulating the environment so radically all the time. And if there's something that can help us get our hands around what we're doing as individuals and as government, I think that's super powerful.
So were you all influenced by her little pitch at the end, if you vote for me? And
No, I wasn't, actually. But.
All right, Peter, your choice, please.
All right. Sylvain.
Sylvain Costas.
Hey.
All right. DNA hack.
Now, I share many of the sentiments with my fellow judges, but I have to say, for those of you who've been touched by disease and your families, the idea of being able to watch an indicator that potentially is very important for your health, and then to be able to actually influence and act in a way that will make you healthier, I think is fundamentally empowering to humankind. So I love the idea. I love the fact that he's already got a company up and running. And I think 23andMe is a nice way to look at a snapshot of who you are, but his technology may enable you to become the human that you want to be, healthy and long-lasting.
Okay,
so,
great.
Here's to you.
So we have the judge's choice, then is Gloria. I'm going to invite all the scientists out now, and we're going to another round of applause, lots of applause tonight, and then we'll reveal, I think we're ready, reveal your vote. So scientists, could you please come out? Now, you can just, so let's congratulate Gloria for at least winning round 1. And was that intentional to have that little, please vote for me thing? Were you in high school a student body person, president or something?
No.
No, you didn't ever done a campaign before?
Political bone in my body. No.
No?
Not at all.
I think you have some future there. Okay. Let's see where we are. Okay. Yes? We are ready for the reveal. And it is going to be, I'm getting very excited. Oh. The popular choice. Mr. Zettel is the popular choice. So it looks like we're going to have 2 Berkeley Lab scientists going to Eureka Restaurant, which will make them very happy. Okay, so I feel like the judges now. Why don't you join us up here on the stools? So I'm curious, judges, do you see, why do you suppose there's a discrepancy? I mean, everything was great, but I'm just sort of curious. Do you have any thoughts?
I think everybody in the audience wants boron nitride underwear.
Okay. So we're going to begin our question and answer sessions now. The mics are here, and there are some upstairs.
I'm curious about the question that you raised yourself, and someone joked at it, but really didn't answer it. I would like to know why you think the audience differed from you.
And you're asking that of exactly all of the judges?
Sure.
Okay.
I'll speak for myself. I think that I am actually a material scientist by background and have worked with boron nitride. I think it's a great material. but I'm very concerned about how much energy is going to be required to generate the volume of material sufficient to make it, architecturally, textile, to make it relevant to an economy. So I would love to find out how we can make great big gobs of this stuff, Alex. So big, huge, fluffy mounds. So that's what I was uncertain about.
Braden, did you have a comment as well?
Yeah, I mean, I guess I come away from this whole thing more impressed with Berkeley Lab than before, and I kind of feel like Alex's presentation about epochs in history was really compelling, and I think we're seeing transformations in all of the presentations. And I guess from my part, I was looking for something that addressed an immediate concern that I have as a citizen, and that's really environmental exposure. And I think both the DNA hacking and the molecular Velcro were going at the same issue. What are we being exposed to? How can we get better control and understanding of that? So to me, as a just an immediate need being met, those were my picks. But I do think that the transformational inventions are super compelling too.
Okay, great. Let's go upstairs. There's a question there.
Sure. It's a little bit more of a comment, but it came out in the Q&A, and I thought was a very interesting observation. But it seems like if you take number 1 and couple it with number 5 and have a really clever device, you suddenly start seeing a lot of things in time, and you see cause and effect, and that seems really cool. So I guess my question is, do you all have like a really big coffee table somewhere where you can like sit around and talk? Because your buildings all seem kind of boxy and isolated. Did you ever get together and like think about putting all this stuff together?
So actually, you spot right on, because the Berkeley Lab has a lot of those roundtable, and I'm in charge of the biomarker project, which is basically looking at not only DNA damage but many other features that's in the blood. We look at body fluid. And this project is also linked with biosensors. So there's many different biosensors. You heard one tonight, but there's all other approaches. So we are working actively on merging those technology and coming up with better programs.
So would you like to add to that?
I agree with Sylvain, and yes, we do have very active collaborations at Berkeley Lab between all buildings and all of the many sites that Berkeley Lab has. So I can definitely see the overlap between both of our presentations tonight, and I think there's some good synergy between, we both are interested in bringing detection out of the laboratory and into more people's hands. So yeah, it's definitely something that we're both interested in.
Thank you for your question. Gentleman.
Okay. This is for Guo Ying. It's probably a selfish question, but as a blissfully ignorant Chevy Volt driver, what is GM doing to prevent the 53 sticks of dynamite from blowing up as I drive the car?
It's a difficult problem, for sure. For small batteries, like those that are not many cells, they normally will use electronic controls, and these electronic controls will just switch off when you reach certain charge state, and so prevent overcharge. But for these larger packs, if you use these electronics, you add up, and it becomes so bulky, and it doesn't make sense, so it doesn't work. Right now, it doesn't really have a very good solution, so that's where we are.
Thank you for your question. Let's take one upstairs.
I had a question about the guilt trip, actually. As one of those crazy consumers who chases pennies down, what's going to be the interface for someone like me with a stick-on sensor on my circuit breaker? Are you guys working on developing that?
So the user interface typically is something called an energy information system, which is a display technology that's often web-based that allows you to consume that information. Most of these data, however, are not actually consumed by people. They're mostly consumed by computers that compute what kinds of faults exist in buildings. So there's not actually very much human interaction with the data. It's mostly handled automatically, and then there's notification to people about faults that are discovered. That tends to be how it works, because if you think about that there's 100 million homes in the United States and 10 million commercial buildings, we're not really going to look at all the data from all of those buildings. We just don't have time for that. So it's mostly automatic, and then you get sort of a pop-up notification on your phone that says, hey, something's going on and you should check it out.
Thanks for your question. Let's go back over here now.
Hi, I have a question for Stephen. I want to know if you have sort of privacy concerns if you want to use this energy measurement stick, for all places.
Yeah, privacy is a major concern with monitoring for a lot of people, and it's something that needs to be taken seriously. So it's something that in my division, so I'm in the Environmental Energy Technologies division, it's something that in my division we spend a lot of time working on and thinking about and working with policymakers on how we can ensure that the data that are generated can be used in a way that benefits society while at the same time not putting people's privacy at risk. And I will say that despite that there's a lot of work going on, it is not an entirely solved problem. But the bottom line is we all agree that it's an issue that we would like to have solved, and we continue to work on it regularly. So right now, the controls are pretty strict, so these data aren't really shared at all. And so that's really kind of the way that it works. But maybe moving forward, we have to find new ways to ensure our privacy and still achieve all the benefits that we're looking for. So thank you for the question.
Thank you for the question. We have just a couple more questions. We have one here.
This question is also for Alex. In your title, you seem to put a lot of emphasis on space exploration for use of your materials. How do you think, though, your materials could be used more for exploration on Earth, like inside of volcanoes, deep sea diving, or also something as simple as using boron nitrate to put into firefighter uniforms, and how that might help that?
So the idea of using boron nitride sort of as a protective material or in space exploration is just one small aspect of the utility. And I tried to mention that in biology and in semiconductor industries, in photovoltaics, in flat panel displays, it could be an essential ingredient. So it's very broad-based. So it's not just for spacecraft, which is a very esoteric type of application. It gets attention, but it's really not broadly applicable. But the materials are very versatile. They can be incorporated into biological or other chemical systems by attaching things onto it. And so it's broad-based from the semiconductor industry, optics, telecommunications, medical industries, energy storage, and water filtration. I tried to touch on a few of those things. It really has an amazingly broad applicability.
Okay, I think our last question for the evening is this young gentleman right here.
This is for the molecular Velcro. I was wondering, where would you put it? Like inside the smartphone or outside? For like, if you're gonna insert like the molecular Velcro, where would it be situated, I guess?
So I was picturing it being inside of the device, and maybe there's like a vent or a fan where the exterior environment can interact with the interior of the device, just like on your laptops or computers. There's a grate where air can pass in and out. Similarly, for like the solution-based assays, maybe if you're doing a test on your own saliva or your own bloodstream, there could be like a little port that you insert your sample into the device.
Oh, and I have another question. If somebody, let's say, doesn't have a smartphone, what would you like? Which isn't pretty.
Well, do they have an iPod?
Well, let's assume like they don't have any, fancy gadgets, I guess, as my parents put it. But they just have like a normal old class Nokia cell phone. How would you use the technology in that?
You're the judge's choice. Go ahead.
We can design a chip for that one, too.
Okay, on that note, we conclude. Thank you, audience. Thank you, Berkeley Lab scientists. Thank you, judges. Thank you, Eureka Restaurant. Please go to the Berkeley Lab website for our notification of our next Science at the Theater. Thank you all for coming.